Hello everyone, I hope all of you are fine. So this is in continuation with what we were discussing in our previous video, and the next topic for the chapter, that is motion in a straight line, is the equations for uniformly accelerated motion along a straight line. Now this topic we've already covered in class 9th, where we derived three equations of motion, out of which first was v is equal to u plus at. I hope all of you remember about that. We derived that equation from a graphical method. In class plus 1 we will be following total three methods and an additional equation as well, that is distance covered in the nth second. So we'll start with the first equation, that is v is equal to u plus at. Now this is the origin point. Origin point is something from where the object has started. At this point, that is x naught, its velocity, let's say, was v naught, and when after time t, means reaching from this point to this point, the time t has passed, the position at this point, it's let's consider it to be x. Okay, so as shown in figure, x naught is the position of the object at t is equal to 0, and x is the position of the object at t is equal to instant t. Okay, so at t is equal to, at time t, the position is x and velocity is v. So this has already been mentioned in the next part, that is v naught is the velocity of object at instant t is equal to 0, and t is equal to 0 is that instant from where the observation has started, from where we have started observing this particle, which is moving initially with velocity v naught, and finally the velocity becomes v after time t. Okay, now velocity after a certain time, that is by definition acceleration is given by change in velocity upon time taken. This we know. So change in velocity would be final velocity minus initial velocity, and final velocity is v and initial velocity is v naught. So time taken would be t minus 0, and this is the definition for acceleration. If we cross multiply with this thing, we will reach to our first equation of motion, that is v is equal to u plus at, or v is equal to v naught plus a into t, where v naught is known as the initial velocity of the object and v is known as the final velocity of the object. Okay, so this is the first equation, and this is also known as velocity time relation. Let's move to our second equation, that is distance covered in a certain time t, that is average velocity. We need to calculate the average velocity in this aspect. So average velocity would be displacement upon time, and the displacement would be final position minus initial position. Final position, as we already discussed earlier, this is x, and initial position is x naught. So after cross multiply this thing, we reach at this point, that is x minus x naught is equal to v average into t. And average velocity can be calculated with the help of taking the mean of initial velocity and final velocity. Initial velocity is v naught and final velocity is v. When we will take the mean of these two velocities, we will reach the aspect of average velocity. Now putting this in equation, in the above equation, that is x minus x naught is equal to average velocity into time, and this is the formula for average velocity, as you can clearly see. When we will cross multiply this, or rather when we will put the value for v naught is equal to, we have derived one equation, v is equal to v naught plus a into t. This we have already derived from equation number 1. We will simply put the value for v here. When we will add in this v naught, so it will become 2v naught plus at into t, and this will be in bracket, of course, in this way. Okay, this is also written, v is equal to v naught plus at has been put in this case. So after simplifying this equation, the position or the displacement, the expression for displacement that we get will be s is equal to v naught into t plus half at square, or in class 9th we wrote it as s is equal to ut plus half at square. I hope you all remember this part, s is equal to ut plus half at square. This is our second equation, and x minus x naught is known as the displacement. So that is why I have written s in terms of this, in place of this x minus x naught, that is displacement. Okay, so this is our second equation, and this is also known as position time relation, as it is written here, position time relation. S is equal to ut plus half a t square, or s is equal to v naught into t plus half a t square. Okay, now moving to the third equation. We know that velocity at a certain position is given by v is equal to u plus at, or v is equal to v naught plus at. So v minus v naught is equal to at. Average velocity into time is equal to displacement. This we've already discussed in the above video, in the above case. So from here, what we'll do is we'll take the value for this v plus v naught. It will be 2 upon t into x minus x naught, and in the above expression we had written this x naught as s, that is displacement. Okay, so multiplying equation 4 and 5, let's check what was equation 4. Equation 4 was v minus v naught is equal to at, and equation 5 is v plus v naught is equal to this 2 upon t into x minus x naught. When we'll multiply these two equations, the left hand side would be multiplied by this left hand side, and right hand side would be multiplied by this right hand side. Okay, so when we'll multiply this thing, we'll reach a plus b into a minus b. It is a square minus b square, the identity we all know, and ultimately from here this t would get cancelled out. So 2a into x minus x naught, and x minus x naught can be again written as displacement, that is s. So v square minus u square is equal to 2as, or v square minus v naught square is equal to 2as, which will be our third equation of motion, which we have already learnt in class 9th by this method, that is the distance travelled in time t before, therefore x minus x naught is equal to displacement, and this is known as velocity position relationship. These names you need to remember: velocity time relationship, displacement time relationship, and velocity position relationship. Okay, so in exam these questions can be asked in this form as well. This is the new equation that we have to derive in class +1, that is distance covered in the nth second. Let us try to understand what is this distance covered in nth second. Let's say the particle is started from t is equal to 0, means from here the particle has started, and particle moves for n seconds. When the particle is moved from n seconds, the distance covered by the particle in n seconds is, let's say, Sn, and 1 second earlier means this nth second earlier. For example, the particle is moved for 8 seconds. We can consider that the particle has moved for 8 seconds. If we have to calculate the displacement of particle in 8th second, so this equation is used for calculating the displacement or distance covered by that particle in 8th second. So what we'll do is Sn minus 1, this is the displacement by the particle covered in n minus 1th seconds. Okay, so what we'll do is, for example, if we have to calculate the distance covered by the particle in the 8th second, so what we'll do is we will try to calculate the distance covered by the particle in 8 seconds, then we will subtract the distance covered by the particle in the 7th seconds, then we will reach the conclusion that from here we can calculate the distance covered by the particle in the 8th second. So in this way, this expression can be used to derive the distance covered by the particle in the nth second. That is, if the displacement of the particle in n seconds is Sn, and displacement of particle in n minus 1 seconds is Sn minus 1, so by using this expression we can derive the expression for distance covered by the particle in nth second. Okay, so let's try how to calculate, how to solve this. So distance covered by the particle in the first t seconds is given by St is equal to S is equal to ut plus half a t square. This is the equation that we all know about, that is the second equation of motion which we derived just now. So what we'll do is we'll simply put the value for t as, means here we'll take t as n minus 1 seconds, since we have to calculate the total displacement in n minus 1 seconds. So we'll simply put t is equal to n minus 1, from here and from here as well, n minus 1 square, and distance traveled by the particle in first n seconds. First n seconds means we will take the value for t as n here, so this is n and this is also n in terms of t. So these are the two equations. Let's say this is the first equation and this is the second equation. Now if we have to calculate the distance covered by the particle in the nth second, what we'll simply do is we will subtract these two. मतलब जितना उसने n seconds में cover किया है उसमें से अगर हम n minus 1 seconds का minus कर दें तो हमारे पास nth second का आ जाएगा. This is the displacement or the distance covered for the nth second. This thing is written as Sn minus 1. Here it is not clear, so you can write it in this way. This is Sn minus 1. Okay. So after that only maths part is there. We will simply put the values for Sn, that is V0 into n plus half a n square, in this way, and from the above equation, that is equation number 1, which we have written, Sn minus 1 is equal to V0 into n minus 1 plus half a n minus 1 square. So when we will simplify this thing, simple maths is there by using the a minus b whole square identity here. This will be a square minus 2ab plus b square, and after simplifying this equation we will reach to this expression, that is Snth is equal to u or v0. I am again repeating it that you can write here and u as well, that is the initial velocity. So Snth is equal to u plus a by 2 into 2n minus 1. So this will be the final expression for the distance covered by the particle in nth second, and in this case we will solve a number of numericals as well. Means for this formula we can solve the number of numericals as well, that is the distance covered by the particle in nth second. For now you try to have a look at this video carefully, and we'll continue it in the next video. Thank you.